Now let's look at logarithmic functions. So first of all, if we look at the exponential function a to the x, remember that graph, as we discovered in a previous video, kind of looks like that. Well, notice that that graph passes the horizontal line test. So it is a one-to-one function. If it's one-to-one, it has an inverse. So we find that inverse by flipping the x and the y. And then to rewrite this exponential as a logarithmic statement, it would look like this. So our inverse function is log base a of x. So a to the x and log base a of x are inverse functions. That means that if I compose them in either direction, I'm plugging in the log as the variable in the a to the x expression, I get back just x. And if I plug the a to the x in as the variable in the log base a of x expression, I get back just plain old x. All right, so let's look at log base 2 of x. If I want to graph that, I would start with 2 to the x and plot some points and draw that graph for 2 to the x. Then remember to get the graph of an inverse function from the original function, reflect across the line y equals x. So sketch in my line y equals x, flip the x's and y's, and these points become like so. For example, the point 0, 2, when I flip the x's and y's, becomes the point 2, 0. Now, let's look at this. Notice that this extends this way. So when I flip across the line y equals x, it'll extend this way. So my domain is only the positive values, because just like this has a horizontal asymptote at y equals 0, this will subsequently have a vertical asymptote at x equals 0. So here my domain is all real is 0 to infinity, and the range of this is all real numbers. Notice that that is flipping the domain and range over here. Over here my domain was all real numbers and the range was 0 to infinity. So that flips between a function and its inverse. Let's graph log base 1/2 of x. We're going to do it exactly the same way. Start with the graph of 1/2 to the x, which is this curve. Flip the x's and y's, and it will generate this curve. Now, remember, the other curve, the exponential curve, looked like this. So this is just rotated across the line, or reflected across the line y equals the y-axis. So when I look at the same thing here, my logarithm that was for the original exponential went this way. So when I flip it again across the line y equals x, it's going to look like so. All right, notice that the domain and the range is exactly the same. That's because the domain and the range of the exponential is still, the domain of the exponential is negative infinity to infinity, and the range is 0 to infinity. And those flip between a function and its inverse. So the domain of this inverse function, the log base 1/2 of x, is 0 to infinity, and the range is negative infinity to infinity. Once again, this is a horizontal asymptote on the exponential, so this is a vertical asymptote when we reflect across the line y equals x on the graph of the inverse function. So a general logarithmic function where the base is bigger than 1 will have this sort of shape to it. The domain will be 0 to infinity, the range negative infinity to infinity. It is increasing and continuous. It is 1 to 1. There is a vertical asymptote at x equals 0, and it'll pass through these points for whatever the value of a is, unless we shift it or reflect it using our basic shifts from algebra. If the a is between 0 and 1, then it has this basic shape to it. Domain and range are the same. Vertical asymptote is the same. It'll pass through these basic points. But it is a decreasing and continuous one-to-one function. All right, let's find the domain of each of these functions. Now notice, with all of the logarithms that we just reviewed, the domain was always 0 to infinity. So if I have the domain of just log base whatever of x being x has to be greater than 0, then that means when I'm looking at something more than x inside the logarithm, whatever is there, I take it and set it greater than 0 and solve for that. So in this case, I would get x is bigger than -3. That's the interval from -3 to infinity. All right, now here, this is not a shift inside the log like this one is. This is a vertical shift. So my domain being 0 to infinity doesn't change when I move the graph up or down. So for B, that domain just stays. X is bigger than 0, which is the interval from 0 to infinity. Let's find the domain of this one. So we'll do the same thing. We'll start with setting whatever's inside the log greater than 0, and we want to solve that inequality. Well, we know to solve a polynomial inequality with the squaring there, we factor, and this factors into x plus 3 times x minus 3, which has two zeros, one at -3 and one at +3. So let's test the sign. If I plug in -4, this would be negative and this would be negative, so it would be positive here. If I plug in 0, this is positive, this is negative, so the interval's negative. And if I plug in 4, this is positive, this is positive, so the interval's positive. So it's positive here and positive here. So the domain is -infinity to -3 union 3 to infinity. We're just omitting where it's negative. All right, now if I look at log base 2 of x minus 5, we can start with the graph of log base 2 of x, which remember, log base 2 of x is equivalent to saying 2, the base, to the power y, the exponent, is equal to what's inside the log. So if I look at just the basic graph of 2 to the y equals x, I can pick out a few values of y and figure out what my x is. So at 0, y is 0, x would be 1, 2 to the 0. So let's write it this way, 2 to the y equals x. Let's pick some values for y and figure out what x is. Notice these order pairs will be backwards. If y is 0, 2 to the 0 is a 1, so we have to point at 1, 0. If I pick the value 1 for y, 2 to the 1 is 2. So at x equals 2, we're at y equals 1. If I pick the value 2 here, 2 squared is 4. So 3, 4, we're up at 2. If I pick -1, 2 to the -1 is 1/2. So at x equals 1/2, we're down here at -1. And so on. So this is the basic graph of 2 to the y equals x, which is equivalent to the statement log base 2 of x is equal to y. Now, how is ours different? This is shifted right 5. So I'm going to move all of these points right 5. 1, 2, 3, 4, 5. There's that new point. Now notice there's a vertical asymptote here at x equals 0 on the original graph. So I move it right 5. 1, 2, 3, 4, 5. That puts the vertical asymptote right here. So all of these points are being shifted to the right 5. Redraw through, it's going to look like that. Now, what's the domain? The domain is shifted right 5 from 0 to infinity would be 5 to infinity. So that's my domain. My range, notice, is still all real numbers. The x-intercept is at 5, 0. And the asymptote, my vertical asymptote, is the line x equals 5. The function is increasing on its domain. All right, now let's look at this one. We're again going to start with the basic graph of y equals log base 3 of x, which we can make into the statement 3 to the y is equal to x, and plot a few points. So again, I'm going to plot my xy points, but I'm going to pick values of y, like 0. 3 to the 0 is 1, so point 1, 0 right here. Pick 1. 3 to the 1 is 3. So at the 3, 1, we have a point here. And pick negative 1 for y. 3 to the negative 1 is 1/3. So at at 1/3, we're at negative 1 on the y. So again, this graph looks something like this. Now, what does this plus 5 do to it? That's up 5 units. So I'm going to move all of those points up 5 units. So this 0 here moves up 5. 1, 2, 3, 4, 5. And now we have a point right there at 1. And then this point would move up 5 as well. So negative 1, 1, 2, 3, 4, 5. But it's over at x equals 1/3. And this point up here at the 1 would move up 5 as well. So over here to 3, we would go up, we started at 1, so 1, 2, 3, 4, 5. There's where that point is. So now draw through all of that. Notice that this is also an increasing function still. My domain did not change because I'm still going from 0 to infinity. The range did not change. I'm still going negative infinity to infinity because shifting it up 5 doesn't change that. And the x-intercept, oh, my x-intercept is now down here. I don't actually know what that value is, so I'm going to have to solve for it. So to solve for the x-intercept, I would go 0 equals 5 plus log base 3 of x. Subtract 5 from both sides, and we get negative 5 equals log base 3 of x. So 3 to the negative 5th is the x value. So my x-intercept is at the point 3 to the negative 5th, comma 0. Now, let's find the inverse of 3 to the x minus 5. So the first thing we do is write it as a y equals statement, y equals 3 to the x minus 5. Interchange the x and y, so x equals 3 to the y minus 5. And now isolate the exponent. So we're going to add 5 to the other side, x plus 5 equals 3 to the y. And now rewrite it in a logarithmic form. So we would say log base 3 of this item equals the exponent. And now replace the y with f inverse. So f inverse of x is log base 3 of x plus 5. Now, let's look at the graph. If we look at the graph of the first function, 3 to the x minus 5, I would graph that 3 to the x has a y-intercept at 0, 1, but we've moved it minus 5 down. So instead of having an intercept up here at 1, we're going down 5. 1, 2, 3, 4, 5. So right here. And then at x equals 1, 3 to the x would be 3, but again we moved down 5, so instead of being up here at 3, we'd go down 1, 2, 3, 4, 5, and plot the next point here. And so on. Now, we moved it down 5, so the horizontal asymptote that was the x-axis would move down 5 units as well. 1, 2, 3, 4, 5. So we would put a horizontal line here and draw our exponential function through those points. And that's y equals 3 to the x minus 5. Now, the logarithm function is log base 3 of x plus 5. Well, we would start with the graph of y equals log base 3 of x. And then this would shift it left 5 units. But to get some points on that, would we write it as 3 to the y equals x? So I would be plotting the points for, pick a y value, let's figure out what the x is. So when y is 0, x is 1. So that's this point here, but I'm moving left 5. So 1, 2, 3, 4, 5, and plot a point. When y is 1, x is at 3. So 1, we didn't actually find that intercept. So let's see if we can find that really quickly so that we have the graph looking a little bit more exact here. That's on this curve. So if I set the y to 0, I'm looking for the exponent that makes 3 a 5. That's going to be less than 2 because 3 squared is 9. So here's x equals 2 over here. Right? So that was just to find the x-intercept. So when y is 1, x is 3. So it's over here. Now it's moving left 5. So 1, 2, 3, 4, 5. That's here at y equals 1. That would be that point right there. Now, also remember, this one has a vertical asymptote at x equals 0, but it's been shifted left 5. So that would be at 1, 2, 3, 4, 5, right here. So we would draw in that vertical asymptote. We can keep plotting points if we want, but we know it looks something like this, right? Going through those points. Now notice the symmetry over the line y equals x. This image and this image would fold on each other in that, if we folded across the line y equals x. All right. The relationship between the two graphs is that symmetry across the line y equals x.